All right, our next talk is by Aimee Merkel, and it is entitled Observations of Mercury's Exosphere from Messenger's MASCS-UVVS.
Right, I'm Aimee Merkel. I'm going to talk to you in a minute about Messenger and legacy of Barth with the UVVS. But
we
I want
can't hear. We can't hear.
Microphone higher.
I was trying not to make it go all crazy like it's been. Is that better?
There.
Okay. So I started at LASP in 1995 as an undergraduate. I'm a direct product of SNOE. I started on SNOE right after they made the they won the award. I started by taking Dr. Barth's SNOE class, and basically if you did really well, you got hired. And so I was really wanted to be on SNOE, and so I worked my butt off in this class. I got hired on. I was so excited to get hired on, and then not only that, but I got assigned to the instrument team. And when Scott was talking about that students built SNOE, we really did build SNOE. It was an amazing experience. There were 4 students on the instrument team, and 3 of us each got assigned an instrument. And unbeknownst to me, at the time, I got assigned the UVVS, which totally changed my direction in my career and has led me to where I am now. The ultraviolet spectrometer is the one in the middle there. Now, Dr. Barth's not in this picture, but he is. Because, us 4, well, really, Mike did the electronics, but Stan Straight, Erica Rogers, and I, that composed of the instrument team, spent countless hours listening to Scott Bailey and Rick Kohner tell wonderful stories about Dr. Barth in the field with rockets. And so I feel like Dr. Barth is in this picture with us. He was larger than life for us. And to hear the stories in the rocket field, we just couldn't ever believe it. That he would have races and go photo driving and go to jazz bars. Okay, so what does this have to do with Messenger? So LASP had an instrument on Messenger called the UVVS, or MASC instrument, which was comprised of 2 instruments. Messenger is mission to Mercury. We just spectacularly crashed into the planet on April 30th. I assume it was spectacular because we couldn't see it. But we were going 9,000 miles per hour when we hit the surface. So we had a direct impact onto Mercury. And what I hear is that we created our own crater, and we will be there forever as little pieces of metal that will melt once the planet turns into the sun. Messenger was selected in 1999. We launched in August 2004. We had 6 flybys, 1 to Earth, 2 to Venus, 3 to Mercury. We went into orbit around Mercury in 2011. I came onto the project in 2010, so about a year before we went into orbit. Bill McClintock is the PI on the MASCS instrument, and because of my experience with the ultraviolet spectrometer, he came to me and asked if I would be interested in working on the mission to Mercury when we went to orbit, and I of course said absolutely yes. So we spent 4 years in orbit, and we completed about 4,000 orbits around Mercury. I include these figures because this is the orbit around Mercury, the first orbit, and then by the time that we crashed, we were way over here. So that's how we moved in orbit around Mercury. Also, this is all the mission operations activity in the last year of the mission. So they kept finding more and more fuel, they kept pumping us up, but you'll notice this is an altitude on this side that we were about 10 kilometers above the surface before we crashed. It was a remarkable feat of engineering and tremendous science discoveries. This is one of my favorite videos of Mercury. This is false color, but before Messenger got there, we had only mapped about half of the planet, and so the entire planet was mapped. And not only that, but one of the instruments, VIRS, that's part of MASCS, was able to take spectra. So on the website, the Messenger website, right before we crashed, they did these top 10 science results and top technological results of the mission. It was, like I said, science success. If you go onto the website, all of these are listed along with a little movie. I didn't put all the movies on here because I only have 10 minutes. So, but some of the important things are, they discovered these hollows, which are these bright features that are inside these impact craters. They think they're related to sublimation processes, the solids turning to directly to gas. It's just really strong evidence that Mercury is still geologically active. There's volcanic deposits. There's polar deposits of water ice in the permanently shadowed regions. I mean, the list goes on and on. So as far as legacy to Dr. Barth, I put together this little chart that shows, starting with Mariner, right, that the spectrometer, right, the 1/4 Ebert-Fasty spectrometer or monochrometer, and Paul Feldman did a very nice talk this morning. Then it kind of split at LASP into two different category of instruments and their optical paths. So started with Pioneer Venus and the OUVS, then Galileo, and then after that there's MASCS, the UVVS. MASCS is the last one of its kind that was built here at LASP, and it was basically directly from the Galileo design. And then we also heard about SME, and then SME went directly into SNOE, which is what I did my PhD on, and we used SME parts to build SNOE. So the MASCS-UVVS and the SNOE-UVS really aren't too dissimilar. Right now, the LASP instrument team, or the science team, is composed of Bill McClintock, Greg Holzflaw, myself, and Tim Cassidy. It's, like I said, very similar to Galileo. Changes that we made that were made from the Galileo design is the weight was decreased from 11 pounds to 7 pounds. They extended the visible wavelength channel. There were 3 channels out to 600 nanometers, which ended up being very, very important because we could get the observation of sodium. There was no off-axis light baffling, and another instrument, the VIRS, was added in the location of the electronics box. So this is one orbit of observations of the UVVS. So you can see my mouse isn't working, but we're wagging back and forth
There's a pointer up there.
We're wagging back and forth here in the night side part of the orbit, and we're coming around, and then we take day side measurements. And we're looking at emission, and in this particular case, we're looking at sodium emission. So we get these limb observations on the day side, and then on the night side, we see this wagging back and forth. So if you were to put this all together, on the day side, we measure primarily calcium, sodium, and magnesium. MASCS was the first to discover magnesium and calcium plus in the atmosphere. We have been able to characterize the day side and of both calcium and sodium, and what we see is that it's very, very consistent and repeatable Mercury year after Mercury year, and is very dependent on the distance of Mercury to the sun. This was surprising because ground-based observations have shown that it was much more variable than that. But after 4 years in orbit, it's highly repeatable. The other thing we'll be able to do is characterize the night side. Mercury has this long tail coming off the night side. So this is kilometers off of Mercury's surface, and in sodium, calcium, magnesium, and you see that at certain times of the year, Mercury year, the radiation pressure is so strong that it blows, basically blows all this constituents out into a long comet-like tail. If we were to put that all together into a movie, this was put together by colleague Tim Cassidy, and this is sodium. So you see the wagging back and forth in the night, and you see the dayside observations in the front. And this is 1 Mercury year of observations. You can see that it gets bright at certain, as you get closer to the sun, and then dims as you get farther away. So the surface, the VIIRS instrument, which Greg Holsclaw in the audience here has been in charge of, they were able to take spectra of the surface and be able to map out. One of the big surprises is that Mercury is thought to have an iron core, and with all the volcanism, they really expected to see a high abundance of iron on the surface, and that is surprisingly not true. There is very little iron on the surface of Mercury. Okay, so back to Barth, just briefly. So the SNOE days, I just think back to them a lot as I continue on in my career. And I'm always in continual awe of the trust and dedication that Dr. Barth put into his students. It really started with him, and it trickled down into the professionals and postdocs. Scott was a postdoc at the time, who mentored us and provided oversight. It's really, truly one of his defining legacies, is his involvement in students. I went through all my pictures trying to find pictures that I actually took, and I came across a roll of film, which was buried because it's not as easy now to get to find these pictures. They're not just on your phone or on a digital computer. And then I had to figure out how to get them into my computer. But so I had a snapshot of Dr. Barth, and this is at the SNOE launch party here in the middle. And I just thought it was such a nice picture of him. Most of these pictures are at the launch party. Well, not all of them. But, when I say we were hands-on, we were really hands-on. I had a picture in here, I guess it was in the previous one. Here, this is LASP's first clean room, and this was right before SNOE was shipped. And anyway, it still flew magnificently. We had no problems. But yet we're all here without any sort of clean room garb on. And then I was so honored that 1998 was a big year. SNOE launched, and I got married. And Dr. Barth and his lovely wife Louise came to our wedding up at the top of Keystone. We had to ride both chairlifts to get up there, and afterwards I asked him, did you have a good time? And he said it was great. We went on this magnificent hike afterwards. So that's just, he's very much missed. He was a very huge part of my life, and just so honored to meet all of you guys finally, because we heard a lot. We heard about you, but it was anyway. Thank you very much.
Questions for Aimee? George?
On Messenger, is the orbit decay consistent with your atmospheric measurements? Or is anything known about why it decayed?
Why did the orbit decay?
Yeah.
We ran out of fuel. We were in an unstable orbit, so Mercury's gravity plus the pressure of the sun. We were we were only supposed to survive for a year, but they kept pumping us up. They kept I mean, the engineers were amazing. They kept saying, you know, oh, we found more fuel. Let's ask for another extended mission. And in fact, they ended up using helium at the end to burst, you know, to pump it up at the very, very end. They found enough helium to give us another month of observations. So, and then at the end, I heard that they found more fuel, but NASA was like, that's it. You can't find any more fuel.
Amanda?
Aimee, about the hollows, is it water ice? And what's the possible connection with geologic activity?
So it's not water ice, and
What kind of ice is it?
it's not. I don't think it is ice.
Oh, I thought you said it was
No, there's water ice in the poles, right? But the hollows are not water ice. And I think that I'm going to refer to Greg here in this one because he's the expert in it. But do you guys know?
They don't know what it is, but I think it has to do with the volumes, they found sulfur, possibly.
Oh, coming from the interior somehow.
Yeah.
One more question, Amy? Or Amanda?
The other A.
So
The
if
other
no iron, then why is it so dark?
So I'm going to refer to Greg again because he really is the expert in this because he took all
They
the
don't know,
spectrum.
still trying to come up with plausible materials that will darken, just darkly.
We need to go back.
Discover carbon on Mercury?
I think that's still,
All right, let's thank Amy again.